Hi, I'm Will Gantt. I'm a PhD student at the University of Rochester, and today I'll be presenting the paper MultiMUC, Multilingual Template Filling on MUC-4. This is joint work with Shabnam Bazad, Hannah An, Yummo Chen, Aaron White, Ben Van Dermy, and Masa Yarmohammadi, as well as a dedicated team of annotators. Template filling is a classic event extraction task where the input is a document and where extracted events are represented by table-like structures called templates. Templates have types and some number of slots, each of which corresponds to a particular semantic role for a given event type. In contrast to most sentence-level event extraction tasks, like ACE 2005, template filling does not feature lexical event triggers. And a template's slots may contain multiple arguments, which may be extracted or inferred from anywhere in the document. This example that I'm showing here is from the MUC-4 dataset, which was developed as part of the Message Understanding conferences in the 1990s, and it is one of the oldest datasets for this task. MUC-4 is focused on incidents of terrorism in several Latin American countries, and features template types corresponding to different forms of terrorism, including general attacks, incidents of arson, bombings, forced work stoppages, kidnappings, and robberies. In the original dataset, each template type has the same set of 24 slots, some of which are string fill, meaning they take entity mentions as fillers, and others of which are set fill, meaning they take categorical values as fillers. However, all contemporary research on MUC-4 focuses on the 5 string fill slots, which cover individual perpetrators, organizational perpetrators, physical and infrastructural targets, victims, and weapons. In total, the dataset features 1,700 documents, split 1,300, 200, 200 between train, dev, and test, where each document may contain 0 or more templates. While template filling has been of significant interest for many years in the information extraction community, resources for the task in languages other than English are still lacking. Thus, our aim in this work was to provide the first multilingual parallel dataset for template filling. Owing to the historical importance of the MUC-4 dataset, as well as its continued relevance to document-level event extraction, we decided to use it for this work. Specifically, we translated the MUC-4 corpus and aligned and projected its annotations into 5 other languages: Arabic, Chinese, Farsi, Korean, and Russian. The first step in this process is, of course, translation. For our initial pass at this, we rely on a strong recent MT system that uses an XLMR encoder in a stratified mixture of experts architecture, which is a variant of the very popular mixture of experts architecture. All documents are translated at the sentence level. To map the annotated templates from English to each target language, we next obtain automatic token-level alignments between the English and target language text using AwesomeAlign, a neural token aligner. Given the token alignments, we can then align template argument spans in the source and target languages. Once the arguments are aligned, the slot and template labels are then implicitly projected by virtue of this alignment. Since the translations and alignments so far are automatic, there will naturally be some errors in the target language data. To address this, we employ 2 types of manual correction. For all data splits, annotators manually corrected argument span alignments. For the dev and test splits only, annotators further corrected the translations of the sentences containing these arguments. All annotation was performed by native speakers of the target language, or else by linguists with extensive training in that language, using a custom annotation interface known as TASA that was built for this purpose. In our experiments, we consider both some recent supervised models that have achieved state-of-the-art performance on MUC-4, and we also evaluate ChatGPT in the few-shot setting. The first supervised model we consider is GTT, which uses a single BERT stack to encode the document text and then decode a sequence of linearized templates using causal masking. GTT held the previous state-of-the-art on MUC-4 before our next model, ITERX, an imitation learning-based model that treats template filling as autoregressive span classification, and which holds the current state of the art. For ChatGPT, our few-shot prompt includes a description of the template filling task, 3 examples of the target language documents and their gold templates, where these examples are selected via BM25 retrieval. In the bilingual setting only, which I'll talk about shortly, we replace the second retrieved target language document with the corresponding English one. Since our primary experimental interests in this work were on the impact of our alignment corrections and on the multilingual training data, we evaluate these models in 3 different settings. In the first setting, we train on only target language data without alignment correction, that is, using automatically aligned arguments. In the second setting, we train on only target language data, but this time with manually corrected alignments. The third setting is the same as the second setting, except that we additionally jointly train on the original English MUC-4 data as well. In all cases, we report results on target language test data with corrected argument alignments. More specifically, we report the CEAF-REE template filling metric, which you can think of as argument F1 for templates. This metric computes an alignment of predicted and referenced templates that yields the optimal argument F1. We also report a variant of this metric called CEAF-RME, which we won't present here, but these results can be found in the paper. Here are the CEAF-REE, or argument F1 results, for all models and settings. In the left plot, we have ChatGPT, in the middle plot, we have GTT, and in the right plot, we have ITERx. The different languages, including English, are plotted on the x-axis, and the y-axis shows the CEAF-REE F1 score. The colors of the bars correspond to the different data settings. The English-only results are in dark blue, the target language-only results with alignment correction are in light blue, the target language-only results without alignment correction are in yellow, and the bilingual results are in reddish-orange. Several observations stand out. First, for most models and settings, we obtain our best target language results in the bilingual setting, training jointly on English and target language data. Second, the benefits of alignment correction for the target language data are more mixed. It helps for some models and languages, but not for others. This may in part be explained by the quality of our automatic alignments. Our automatic alignments didn't actually require very much correction. Lastly, the results on English are substantially better than those for any non-English language, suggesting that there is still much room for improvement, potentially with language-specific models. We additionally conducted a detailed error analysis on the outputs of the GTT model. We used the template filling error analysis tool of Das et al. For this purpose. Given an optimized alignment of predicted and reference templates, this tool converts the set of predicted templates into the set of reference templates via a sequence of transformations, including insertion and deletion operations for templates and role fillers, and edit transformations for entity mentions and their roles. Different error types are then defined based on these transformations. Here are the results of the analysis. Consistent with past findings, we observe that missing role fillers, shown here in light blue and light green, account for the great majority of errors across languages and data settings. This is unsurprising, given prior work showing that template filling models tend to struggle with recall. Our paper, the MultiMUC data, and code are available at the following links. Thanks for listening.